welcome. In this video we are going to implement the famous NeRF paper. So this is a great paper because it does not require camera parameters as opposed to most NeRF paper. So you can just put your images in a folder and then run the algorithm on that folder, and you will learn at the same time the NeRF model on the camera parameters of your cameras. So that's very simple. You don't need to. There is no more friction with call map on with handling your files, on formatting them. Sometimes on some dataset the result can be a bit blurry, but generally speaking the results are very great. These are the results we'll get by the end of this video. So on the famous front dataset, so you just put your 20 images in a folder, you run the algorithm, and these are the kind of novel view you can render after training. So very good, very impressive on this. Let's dive directly into the implementation. As usual, we'll use PyTorch to do the implementation. We're also using Matplotlib for plotting the results, Glob for loading the images, on NumPy for implementing a few helpers. Okay, so let's dive in. We can start by implementing the NeRF model. So as usual, we are going to do positional encoding. So we take as input the dimension of the positional encoding for the position and for the direction, as well as the hidden dimension for the MLP. So the NeRF model is made of several blocks. For example, because in the middle of the network we feed it the position again. So it's kind of a skip connection to make sure that the information does not get lost in the process. So with a few blocks, maybe that will be a bit clearer when we implement the forward function. We are storing those dimension, the dimension for the positional encoding. We'll come to that in a moment. Okay, so first thing first, we can implement the positional encoding. So that's very easy. We take as input x, that can be either the position or the direction. We take the dimension, so to which extent we want to do the positional encoding, and then we can directly apply the equations from the initial NeRF paper. Unusually, as often it's not mentioned in the paper, but we also keep x in the positional encoding. So we do the positional encoding, which can be written gamma of x, and then we concatenate x to these results. Usually that leads to better results. Now we can implement the forward function. So the first thing is to embed x on d, so the position of the direction, to higher dimensional space through the positional encoding, and that's why we needed the dimension of the positional encoding. So first we feed the embedded position to the first block, and then once we get a feature out of it, we concatenate again this feature with the embedded direction, with the embedded position. So we are doing a skip connection in the block 2. So that gives us a feature. And then out of that feature, we extract the sigma, so the density, on again h, which are the other features that are untouched. And then we can feed that to the block 3 and block 4. So basically, block 3 and block 4 could have been written in a single block. But so first we get the density that is not dependent on the direction, and then we out of this hidden feature. On the direction, we get the color. So basically, we take as input a position, a direction, and we output a color on the density. The density is not dependent on the direction as opposed to the color. Now we can move on to the compute accumulated transmittance function. If you are following my channel, that's a bit redundant. Now you are getting used to this function. If you are new to the channel, this is just a simple implementation of the equation in the initial NeRF paper. I have a full course on Udemy about it. Maybe you may be interested about it. I will put the link in the description if you want more mathematical detail about it. But otherwise, that's just an implementation, strict implementation of the equations from the initial NeRF paper. Now we will do the rendering. So we are doing volumetric rendering. Again, if you are following my channel, you should be you know this function. And again, this is detailed in my course in case you want more detail. But otherwise, this is a very simple function, just a few lines of code and very easy to understand. So first what we do, we sample some points along the way. So we sample points t, so uniformly, and then we do perturb sampling. So we sample them randomly. We do we add some perturbation to the deterministic point t we've sampled, so that we do not always sample at the same points, so that there is no overfitting. So the first thing we do is first we sample t. We also compute delta, so the difference between each t, so that we can use this value when we do the Monte Carlo integration. We'll come to that in a moment. And then when we have t, we can really compute what interests us is x. So along the way, we'll sample a few points randomly, and that's y, and that's how t is used. So given the origin of the ray and the direction, we can compute the position of the ray at a given time t, and then compute the position what we really want. And we can also compute the direction of those points. For all the points along a ray, the direction is the same. So we just need to expand the ray direction so that it will have the same shape as x. So batch size, comma, number of bins. So for each ray, we have number of bins points, and then comma 3 because we have a 3D vector. So once we have x on the direction, we can feed that to the NLP model, to the NeRF model, which yes, it is basically a MLP, but let's call that the NeRF model. We feed the position, the direction, and we get the color on the density. Then we can compute alpha. Again, this is just a strict implementation of the equation from the initial NeRF paper. We can compute the accumulated transmittance function with the function we've created, and then we can do the Monte Carlo integration and compute this integral. So we approximate the volumetric integral with a finite sum with it's not a Monte Carlo integration, sorry, it's a quadrature basically. So a very simple quadrature to estimate the integral. Then we can move on to the training function. The training function is very easy. Basically, it's just supervised learning. So we have the ground truth, we have the target values, which are the pixels from our training images, and we have our prediction. So basically, this is the prediction made by the model on the given the ray direction on the ray orientation. So okay, let's dive in the code. That will be it will make the understanding better. So we iterate over the number of epochs is in standard machine learning. Then we will during each epoch we will iterate over all our training images. So we shuffle our training images, and then we iterate over each image. So we sample a batch. So given in a given image, we sample some rays, so some pixels. For those pixels, we get the origin and the direction. We also get the sample. So I think So we get the origin, we get the direction, and we also get a sample IDX. So basically, these are the pixel IDs that are associated to those rays. And that will be useful to know, to get the ground truth pixel values. So ray origin and ray direction, they have the shape of the batch size, and therefore, but the training images, its shape is h times w, and thanks to those pointers, sample IDs, we can get the ground truth pixel values. So first thing first, we sample a batch of origin and direction. We will implement this function in a moment. Then we get the ground truth pixel values. Then we compute the prediction from the model. So we do a rendering. So we render rays with the render ray function we've just created using the NeRF model on the ray parameters. And then we take the MSE loss between the prediction and the target value. So it's very simple supervised learning algorithm. It's just that here we do not call the model directly, but we need to have this rendering function. But just strictly speaking, supervised learning. Then in this case, we have different optimizers. We don't have a single optimizer. It's because we have one optimizer for the neural network and also optimizers for the camera parameters, the intrinsics and extrinsics parameters. So we have 3 optimizers. But this implementation is generic. That means that you could have only one optimizer. You could have 10 of them. So yeah, you will take a list of optimizer instead of a single optimizer. So yes, very standard in PyTorch. We set back the optimizers to 0, so we clean the gradient, we do the backward, we do the backward pass, and then we do the optimizer that step, so we update the weights of the NeRF model. We can log the loss, and also we can use schedulers to improve training, so reduce little by little the learning rate during training. Now we can move on to the test function. Again, if you are following this channel, you are aware of this function. A few modifications with this sample batch that was specific to this NeRF implementation. So what we do, we sample the origin and direction of the rays in the image. This time we don't need the index of those rays because we do not sample them randomly. We use this parameter sample all equal to true. That means that this time we sample all the rays in the image. If we try to do a rendering of those rays, we will have CUDA out of memory because that will involve sampling millions of points. So we will have, let's say that H and W are equal to 400. We will have 400 by 400 times 400 times 400 pixels. So that's already a lot. And for each of those pixels, we will have to sample a number of bins points. So by the end, we will have hundreds of millions of points to sample to send to the NeRF model in this line. So line 67. So X, we will have millions of points X, and when we send that to the NeRF model, we'll have a CUDA out of memory. So we'll need to do a batching. So we will chuck those tensors, and we'll compute the pixels batch per batch. So this is what we are doing. So line 110 and 111, we do the batching. Then we compute the pixel values for those batches, and then we append the value in the data structure data. And then we can put everything together to create the final image, and we can save it. We can save it in our hardware. Okay, so far so good. Now we can add a few helper function, and then we can put everything together and start training. So we can create a function to initialize the camera parameters. So in this case, we don't need files of camera parameters. They will be learned directly. So we will just initialize the intrinsic parameter to 1. So basically, this will be the focal length. So in this implementation, we're assuming the same focal length for the X and Y axis. It's not always the case. So for example, you could use two values if you wanted to learn a value for fx and a value for fy. And then we have the camera extrinsics, so the rotation, so the position and the rotation of the camera. There are different ways to parameterize that. In this case, we are doing it with 6 values. So 3 values for the position and 3 values for the orientation. This is described in the paper, I think in section 4. Yeah, so this is this equation. So basically, the camera poses are parameterized by phi or by w. It depends how you write it, but basically it's represented by a 3D vector. So we need 3 values for the direction, 3 values for the orientation. We'll come to those equations in a moment. But basically this SO3 is a well-known representation in computer vision, and this is a nice way to do some optimization of the camera parameters. Some optimization are better than some parameterization are better than others, and will make the optimization problem easier, and will help convergence. Okay, so once we've created this function to initialize the camera parameters, we can load our images. So very simple, just we give a data path, just a reading image per image in this directory, on putting all this in a NumPy data structure, on returning the NumPy data structure. So yeah, nothing complex, just reading the images in a file. Now comes this function, get NDC rays. So because of the scene we've chosen, so this one, which is a real scene, the rays can go, when we shoot rays in the scene, they can go from t equals 0 to maybe t equals 10, 20. We are not really sure about where is this wall in the background. Sometimes you can have unbounded scene, so t can go up to infinity. So basically, get NDC rays, we'll take rays, and we'll do a ray transformation so that the rays are in a box that is bounded. So basically, t that goes from 0 to infinity will be shrink to in a box where t goes from 0 to 1. So we're doing a transformation so that we can we can optimize for unbounded scene or for forward-facing scenes like this. This implementation is just implements the equation from the initial NeRF paper. So yeah, it can look complex if you go in the NeRF paper in the appendix. This is a strict implementation of the equations. If you were if you run this code on for example, let's say synthetic data, let's say the Lego scene from the initial NeRF paper, or on your own data, but in a way that you are taking a 360 images of your object, then you don't need this function and you can remove it. Now we can implement this sample batch function to sample the batch and send them to sample the batch during a training, and then we will be done and we can put all the pieces together. So given we take as input the camera parameters, the batch size, also the training images, the size of the training images. Maybe that's a bit redundant. Maybe we could get those values from the images. The image index. So either we provide the image index. Let's say I want to sample rays for the image 0, or we can say sample all equal to true. In that case, image index will not be used and we will sample. Oh no, I'm sorry, that's different. Image index says from which image we want to sample rays. Let's say image 0. On sample all will tell us if we want to sample all the pixels or just a few of them randomly using the batch size. Okay, so let's say we want to sample all pixels from the image. So image indices, it was an integer. We just make it a tensor that will have the same shape as u and v. So u and v, basically these are the indices of all pixels in the image. So we are just doing a line space between 0 and w, on 0 and h, and then we are doing a mesh grid. So basically u and v will be a grid of all the pixel values. On image indices, it's just a tensor with the same shape as u and v, and with the same value everywhere, just the image index. And we do that because it will make the some other operation later easier or more efficient. And otherwise, if we don't want to sample all the pixels, we just sample a few of them randomly. So again, image indices, we do exactly the same. And then for u and v, instead of doing a mesh grid, we just sample them randomly. Now we can retrieve the focal length from the intrinsic parameters. So instead of just saying the focal length is equal to the camera intrinsics, we use this formula. We do a reparameterization that makes the optimization easier, and this is mentioned in the paper. Then we get the position of the camera. So the position is just the first 3 values of the camera extrinsics, and then the rotation is the last 3 values. And then from this rotation, so this vector R, we will get the camera toward the matrix. So first we can compute the phi skew operator. So if we come back to the paper, this is this operator with the at, the skew operator. This is a well-known operator. You can search for it on Google. You will see. So basically, it's just a strict operation implementation of the skew operator. So once we have phi skew, as mentioned in those equations, so phi skew, we can compute the matrix error by using alpha, which is in our error vector. So basically alpha is the norm of the error vector, and then we can compute the matrix error by just implementing the equation from the paper. And then we can compute C2W, which is just the 2W matrix with the so there's a 4x4. So the R matrix is a 3x3 matrix, but C2W is a 4x4 matrix, where on the leftmost part, on the upper left part of the matrix with the R matrix, and on the top right with the position, so the vector t. And for the last row we have just 0, 0, 0, 1. So this is the standard way to represent C2W matrix. Okay, and then from the C2W matrix we can compute the direction of the rays. Again, that's a common way, on a standard way to compute the direction of the rays from the camera. So maybe you can read a bit more about computer vision if you want to learn more about these equations. They're also treated in my course in case you want to learn more about them, but otherwise you can just accept this implementation as it is. So once we have our rays, so the origin and the direction, just using those equations, we can transform the rays to NDC rays again, so that we can optimize for unbounded scene. If you have a bounded scene and you don't need this NDC, you can just comment line 182. And we normalize the rays. So usually in ray tracing, we make sure that our rays have a norm of 1. So yeah, just using this function for normalizing the rays. Okay, and now we can finally put everything together. So we'll use 1e to the 4 operation, so 10,000. Depending on your hardware, it will take maybe between 8 and maybe 15 hours. Yeah, it's an old paper, so now we are used to NeRF paper that train in a few seconds, in a few minutes. This is still the vanilla NeRF with a few improvements, so taking a bit of time. Okay, so first we can load all the training images by using the load image function. Then we can initialize the camera parameters. We create the batch size, so 1024, that's common in NeRF. So in the paper, they train in 2 parts. So first they train the model, where they learn at the same time the 3D model on the camera parameters. And then, but that can sometimes lead to blurry results. So once we have learned the camera parameters, we train a second time by just optimizing the NeRF model. So for this first part, we create the NeRF model, we create an optimizer for the NeRF model, we create optimizers for the camera parameters, and we create schedulers, so a scheduler for the model and schedulers for the camera parameters. Then we can launch the training function, so train the NeRF model on the camera parameters on this. So for the NDC rays, we use a near plane of 0 on a far plane of 1, because yeah, all the rays from t that goes to 0 to infinity will be contracted in a bounding box of where t max hf is equal to 1. So if you are using NDC rays, it will not be useful to push, for example, to use 2 instead of 1. But let's say that you comment line 182, then you need to set the appropriate value as a function of your scene. Okay, so this is the first part. Now we can move on to the second part. So we'll just do roughly the same, but now we'll just train the NeRF model. So we are initializing it again. We'll retrain it, but from scratch. So we initialize a new NeRF model. We create an optimizer for this new NeRF model, a scheduler. But this time we only optimize this NeRF model, and we are reusing the camera parameters from above. So you see this time for the list of optimizer and the list of scheduler, we give only one optimizer on only one scheduler. On our training function is generic, so it can handle either a single scheduler or 3 of them, as was the case on line 207. Okay, so I really hope this video was helpful to you, that you liked it. Please let me know if it was the case. If it was the case, also leave the thumbs up. It will help with this channel, and subscribe for more video related to NeRF. Thank you.